that takes us to chapter 11, and the good news about chapter 11 is there's actually not a lot new with chapter 11. Chapter 11 might be in some ways the easiest chapter because it doesn't have much new at all. It's actually a lot like chapter 9, and I'll explain in a minute. So this should be probably a shorter um, video series or video lecture. But so introduction to repeated measures designs. With repeated measures designs, one group of participants is measured in two different treatment conditions. So in chapter 10, we had two samples, um, and they're separate. So we might I'll bring back the reading group enrolling in a reading program, a group that didn't take the reading program, a group that did take the reading program. Chapter 11 is we get a group of people, a sample of participants. We test them before the reading program, and then we test the same group after they've taken the reading program. So it's one group of people tested twice. That's what we're looking at. All right. So this is really the only big difference. The only big difference is D-scores. Other than D-scores, this is, like I said, just like chapter 9. So if we go to my math video game example, which I know I've used in the past, again, we'd have one sample of students we test before they played the video game and after they played the video game. So we have two scores, and we're actually going to find the difference. So we're going to take that second score and subtract the first score. We got 5, we got 2, -2, and 3. And we're going to actually use this list of scores, just like we did in chapter 9. We had a list of scores. Here's our list of scores. So let me just kind of, I'm going to go through an example. Let me go through an example here. And I'm going to show you a problem in chapter 9, and then how that problem would look in chapter 11. And you can see it's almost the same with just a few differences. So chapter 9, we had the single sample t-test. So we had one sample. And then in chapter 11, we've got a sample that we're testing twice. We're finding the difference, and that differences between the before and after, we're going to treat just the same way that we treated the single sample test before in chapter 9. So hopefully when I go into the details, the concrete example, this will hopefully light up inside your brain. So in chapter 9, a problem might be like this, a single sample problem. Sample of 36 college students enroll in a reading program. They then take a national reading test. Their mean scores on the test is 82 with a sample variance of 9. National average for this reading test is 78. Does the reading program have a significant effect on the reading levels of college students? Okay, so again, what we have here is we get a sample of students, and they enroll in the reading program. We test them. We compare their test scores with the national average. Problem with chapter 11: very often we don't have information on how the population does. So what we can do is we can just take two samples and compare them. So sample of 36 college students taking a reading test, score 77. Same college students that enroll in a reading program take the reading test a second time, and their second attempts they score an 82. So does the reading program have a significant effect on the reading levels of college students? So in chapter 9, we didn't have the standard deviation. That's how it's different from chapter 8 when we had the z-score. That's why we're doing a t-test. We don't know the population standard deviation. But here, we don't know anything about the population, the standard deviation or the mean. So chapter 9, you're comparing a sample mean to a population mean, sample mean to a population mean. In chapter 11, we're comparing two sample means, one without the treatment on the left, one with the treatment. Notice we don't know anything about them. How do you calculate standard error? You use the sample variance and n as per the formula. The way you calculate standard error is use the variance of d and n, and so we need the d scores. Here's an example of the d scores right here. Tested before, tested after, the difference between the two scores. There is the d scores. Okay, so this is the way it looks. So let's just kind of go through. Let's say the mean was 86 with 6 participants. Let's say here are the means for the sample before they took the reading program, after they took the reading program. Now this is the only real part that's different. The only real part that's different between 9 and 11, as I've said, is we make a list of difference scores. We make a list of difference scores. Here's the list of difference scores. The second score minus the first score gives us the list of difference scores. You calculate the mean and variance of that list of difference scores. Calculate the mean and variance of, what is the mean and variance of this? And that's what we're going to use instead of the mean and variance of the population or a single sample. So notice from here on out, it's the exact same structure. The mean is 82, variance is 6. Let's say we have a mean of 5 and 7.1. Why is the mean so much smaller? Because the difference between the scores, whereas on the left it's the scores. So notice standard error, square root of the variance divided by n. Standard error, square root of the variance divided by n. It's the same, different notation. T, notice it's the same thing. M minus u over the standard error, m minus u over standard error. So it's the difference scores. So just to be clear here, it's the average of the difference scores minus the expected average, and the expected average, null hypothesis is there's no difference. There's no difference between before and after, so that becomes a 0, divided by the estimated standard error. So again, incredibly similar. And this might be surprising. Degrees of freedom is n minus 1. Why isn't it, since we have 2 sets of scores, why wouldn't it be 2n minus 2? Because we only still have one list of participants, and that's what degrees of freedom is referring to. We only have not the number of scores for each participant, but we just have one list, one set, one sample of participants, so it's n minus 1. And then hypothesis test is going to be the same. We find that degree of freedom. We have 6 participants, so in both cases it's 5. And then, if it's a 0.05 and two-tailed, we're going to reject that null hypothesis because we have a very large t-score. The good news is I've already said almost everything that's in here, in this chapter. So I've already gone through here how you get a d-score. I've covered this material. This is pretty much what we've been working on. I explained the hypothesis. I'm not going to go into any detail because I would just refer you back to chapter 9. Effect size, there's not much difference at all. Here's the key thing right here. To find the Cohen, so again, Cohen's d is always standard deviation, always the difference between the two means divided by the standard deviation. And that's d is the difference, the average of the different scores divided by that standard deviation, the standard deviation of the different scores. Percentage of variance accounted for is the exact same thing, as is confidence intervals.